everybody, welcome back. So today is going to be the second video to that set of notes that we started with sex-linked traits. So today I will be moving on and talking about pedigrees. Should be a pretty short video. I only have 4 slides, but I'm going to walk us through what are pedigrees and how can we use them to analyze inheritance. And so ultimately a pedigree is simply a genetic family tree, right? So some of you may even have family trees that you have for, at home, documenting, right, your generation, your parents' generation, your grandparents' generation, and then so on back to whenever the earliest information you have for your family is, right? And it might look something like this. Obviously probably with more information with names and such, but it's showing, right, the relationship between people who are married or partners, their children. It shows sibling relationships, right, and you can trace these relationships back through generations. And we kind of talked about this actually in our evolution unit. But you can also think about how much of the DNA in each generation is being passed down through each offspring, right? And so pedigrees are represented using shapes, and so it makes it a little simpler, easy to read, especially when it gets quite large. And so they'll often look something like this. They'll have the individuals numbered in each generation, and the generation is usually labeled with a Roman numeral, right? And so this would be the first generation, individuals 1 and 2, the second generation, individuals 1 through 5, and then the third generation, individuals 1 through 6, and then the third generation would be the youngest generation, right? So grandparents, parents, grandchildren, okay? And so more specifically, a pedigree is showing which individuals express a certain trait. So something that is being genetically coded, the pedigree is going to show inheritance of that specific trait. Okay, so we have individuals that express the trait, individuals who do not express the trait, and then some individuals who are carriers for the trait. And I talked a little bit about carriers in the previous video, but carriers are going to be heterozygous, right? And so they would have one copy of the recessive allele, but they don't show the trait. They're just kind of carrying it secretly. And so here's an example. This one's not fully labeled, but it's showing color coding for normal versus carrier versus, in this case, hemophiliac. So hemophiliac meaning someone who has hemophilia. And if you don't know what I'm talking about, then definitely make sure to watch the hemophilia video that I have linked, and I believe it's the check-in for the 25th. And so in this case, right, you can see here a circle, it represents the females, okay, and so having just the light yellow would be normal. And then having the half yellow, half orange would be carrier, and then fully orange would be having hemophilia. And then normal male versus hemophiliac male. And there's no carrier males, right? Because males only have one X chromosome. And so whatever allele they have on that X chromosome is going to dictate what trait they have. So they cannot carry it. They're going to either have it or they don't. All right. And so these last 2 slides are just going to be for us to practice working through pedigrees because they're, like I said, really good tools for us to track inheritance, but we can actually also do some deduction if we understand pedigrees, and we can actually be able to fill in the genotypes based on the information that we're getting just from these shapes and colors. And so we'll start with one that is hopefully a little simpler. And so it's going to be a trait that is autosomal dominant. And so if you recall, autosomal refers to a trait that is on the first 22 pairs of chromosomes. Okay, so all the non-sex chromosomes. And then it's going to act in a pretty simple manner of either it's dominant or it's recessive. And in this case, the trait is dominant. And so I have here just a little key. Black shapes are individuals that show or express the trait. And then the white shapes are individuals that do not show the trait. And so the black shapes are going to show that dominant trait, whereas the white shapes are going to show the recessive. And so we can actually begin to fill in the genotypes. You could almost think of it as being kind of like genetic Sudoku. And so if I have done my animations correctly, then I should be able to walk us through this pedigree, filling it in. And so what I always start with is filling in the recessive individuals, because we know that there's only one possible genotype for recessive traits to be expressed, right? They're going to need both of those recessive alleles. And so I'm going to use B for my allele letter today. So let's take a look. All these white shapes should be recessive, and so they should have a genotype of little b, little b. So let's see if that's the case here. Right, okay, great. And so we can go ahead and fill in all the white shapes with having this little b genotype, okay, because that's going to give them that recessive trait. All right, and then now we can start thinking about the black shapes, right? Because black shapes represent the dominant trait. However, if you recall, dominant trait can be coded for either with a homozygous dominant, so big B, or it could also be heterozygous dominant, so it could be big B, little b, because dominant traits only need that one dominant allele to be expressed. So we have two possibilities, and this is where we're going to have to start deducing things. All right, and so I'm going to pick actually a family. So you can see here, individuals 3, 4, 8, and 6 form a family, right? So these are the parents and these are the children. And the reason I'm picking this family first is because they have a recessive trait expressing a family member. Okay, and so if we think about it, this offspring, individual 8, has little b. So it's going to get a little b from individual 3, the mother, and it's going to have to get another little b from individual 4, who's the father. And so individual 4 is going to have at least one little b, but it's showing the dominant trait. And so it's going to have to be heterozygous. Okay, so let me see. I think I have that in there. Good. Right, and so we've figured out the genotype for individual 4 by kind of backtracking from their children. Okay, all right, and then we can actually also do the same for individual 9, who is the other child in the family. Okay, and so individual 9 shows the dominant trait, and it's got to get at least one little b from mom over here, right? Because mom only has little b's to give. And then again, it's going to have to show the dominant trait by having at least one dominant allele. So individual 9 also needs to be heterozygous. All right, so we have this part of the pedigree filled out. Now we can pop on over here, and then we can see here this family, which consists of individuals 1, 2, 5, 6, and 7. They also have a family member who is recessive. Okay, and so individual 7 has little b. And it's going to have to get those from its parents, right? And so that means individuals 1 and 2 each have to have at least one little b to give to individual 7. But they show the dominant trait, right? So again, you can probably see where I'm going with this. Individuals 1 and 2 also have to be heterozygous. Okay, and you can see there, and then that way they can maintain that dominant trait while still having that recessive allele to be able to give to individual 7. Okay, and then now this is where it gets a little tricky. Okay, so individuals 5 and 6, which are the children of 1 and 2, they have the dominant trait. Okay, but there's no real telling unless we are given new information about their children, whether they're going to be heterozygous like their parents or they're going to be homozygous dominant. Okay, and so there's no real way of being able to deduce this. And so that's why I have them filled in as they either could have 2 big B's or they could be heterozygous. So there's, like I said, no real way of telling until we get more information about their offspring. All right, so this would be how you can fill out a pedigree. And so I believe you should have this on your notes. So if you're following along on the note sheet, then I would make sure that you have this filled out. And if you don't have it already, feel free to pause the video here and write it down. But I'm going to move on to the next pedigree, which is going to be also on your note sheet. So let's take a look. Now this is a new type of trait, and so you want to make sure that you're paying attention to what kind of trait it is, all right? Because the previous one was autosomal dominant, okay? But now we're talking about an X-linked recessive trait, okay? So it's not going to be on that first 22 pairs. It's on the X chromosome, and the trait is recessive, not dominant. And so again, the black shapes show the trait, and the white shapes do not show the trait. But this time the trait is recessive, okay? And so that means these black shapes should all be recessive. And again, recessive traits must have the recessive allele, right? And so we can fill in the black shapes first, okay? For the females, right, circles are females, they're going to have 2 copies of that recessive allele on each of their X chromosomes, okay? So they should be X little b, X little b. The males, which are the squares, they only have 1 X chromosome, so they just have to have that 1 recessive allele on their 1 X chromosome, and they'll show that recessive trait. So it should look something like this, okay? And so, again, right, the female should all be X little b, and then the male should be X little b, Y, okay? And again, the gene that we're talking about is not on the Y chromosome, so we're not attaching anything to that Y. Okay, so we have our recessive individuals filled in, and now we can do the same as we did with the previous pedigree and kind of backtrack. However, with X-linked traits, we have almost a little bit of an easier time in a sense, because we can first fill in all the males, right? Because the males, either they're going to have a big letter or they're going to have a little letter, right? Because they only have the 1 X chromosome, so there's no combinations that you can make. And so males, right, so white shapes again are showing the dominant trait this time. Males with the dominant trait should have that 1 copy of the dominant allele. So we can actually go ahead and fill in those dominant males first. Okay, we don't have to do any deducing really, right? So they should all be X big B Y. All right, so now we can focus on some families. And I'm going to first look at this family where 1 and 2 are the parents. Okay, and it's 4, 5, 6, 7, and 8 are the offspring. And so we filled in all but 4 and 6. And so 4 and 6 are females that are showing the dominant trait, okay? And so they're going to have 2 X chromosomes, so they're going to have 2 copies of this X-linked recessive gene. And so we can take a look at their parents to figure out what their genotype is going to be. All right, and so X little b from the mom, and then X big B, Y from the dad. Now the mom has to give one of her X chromosomes, right? And she only has 1 possibility, X little b. Now in order to make a female child, the dad has to contribute either the X chromosome, okay? And the dad has X big B. And so if we combine those 2 together, we can figure out that these 2 daughters are going to have to be X big B, X little b. And then in this way that they're going to show that dominant trait. So they do not show this recessive trait, which is why they have that white color. And in fact, you can be even more specific and you could fill them in half to show that they're carriers. Okay, so that's that first family. And then now we're left with 10 and 12. And so these are daughters who do not show the recessive. So in other words, they are dominant. Okay, and if we look at their parents, and again, this is going to be a little tricky, right? The father has an X big B to give. So they both are at least going to have 1 big B, okay? But the mom has 2 different options, right? She's heterozygous, right? So she's got a big B and she's got a little b. She could be giving either of those to 10 or 12. We don't know. Again, right? We wouldn't be able to figure it out until we got more information about 10 and 12 as possible children. And so this is going to be similar to those last couple individuals that we had in the previous pedigree. We're going to have to kind of leave them open-ended, right? They're going to either be big B, little b, or big B, big B. We're not going to be able to know for sure. Okay, and so again, I would make sure to fill this out on your version if you're following along on the notes. But this is how we use pedigrees in genetic analysis. It's pretty useful to track genetic diseases in particular. Okay, when genetic counselors are talking with families, right? That's why you might get asked on a medical questionnaire about if you have a history of certain disorders or diseases in your family, because we can piece together this familial information in a pedigree and kind of figure out, what might be the different possibilities or chances of someone else in your family having disease or any possible children. Okay, and so we'll come back to using pedigrees hopefully in the future, but this was just my introduction to what they are and how we use them. Hopefully it was pretty straightforward this time. And again, if you have any questions, just let me know, and I will also be posting some more practice as well. All right, so I will see you next time. I believe the next video that I have planned is going to be about mutations, which should be quite fun. Okay, so please look forward to that. And again, I'll see you next time. Bye-bye.